Hello and welcome back. So at this point we have generated our structural grids and we have brought in our petrophysical results or written those out internally to a log database, and now we're ready to start with the 3D property modeling. So in Danomics we have tried to make the 3D property modeling very approachable, and we build our 3D property models through flows. So what we're going to do is we're going to right click on our project folder. We're going to say new flow. And let's say at first I want to make a porosity model. So I'll call this pht vol.flow. Hit OK. And we need to start off by bringing our well log data into the flow. So I'm going to start with a log input. And I'm going to grab the interpreted LAS database that I had. Okay, so once I have that, I'm going to click New, and now I'm going to choose my Logs to Volume tool. This is what generates the 3D property model. And I'm going to grab my structural grid, and I'll need to decide what zones I want to use. So how you set the zones will determine the layering. I'm going to choose the Lewis as the top. I'm essentially going to choose most of my zones here. These are just the major formations. But if you were to have lots of subzones, you may want to consider omitting some of those for the modeling process. So we need to choose these zones in stratigraphic order here. That's important. We then choose our well headers, and we'll choose our curve. So here we're going to choose the total porosity. And we have several different interpolation methods. We have kriging, splining, inverse distance. I'm going to take a very simple approach for here. I'm going to use a linear interpolation. And now probably what's the most challenging part of this for most people is deciding on the geometry. So I'm going to click on Initialize Grid from Files, and I'm going to choose my well database. Now, what I see here when I choose this is, okay, it's based the origin X and origin Y off of our data. It's looked at, the extents, and it said, hey, we need to, we're going to have 8,000 inlines and 4,000 cross lines. That would be a very, very large model. It would take a substantial amount of time to run. And this would be made on 100-foot spacing. And that's just very inappropriate given the coarseness of the data that we have here. We are going to run this on, let's say, 500-foot spacing, which still, given our data, is very, is very dense. And now we see this has came down to 1,600 inlines and 800 cross lines, so much more modest. Now notice you'll see when we run this, our data doesn't actually cover the full extent of that, but that is okay. So now we'll hit OK, and that populates these parameters. The next thing that we'll need to choose is we'll need to choose the top and base elevations for our model. Now this is another area where people often ask me, how do I determine this? The way that I like to do it is I come over here to my structure grids and I open those up, and I go to the topmost formation, so the Lewis. I say show me the color bar, and I look and I see, hey, what's the shallowest depth that we have here? The shallowest depths are just a bit greater than 2,000 feet TVD sub C. So that's above sea level because the elevations here are quite high. So I'll come back over here to my flow and I'll put the top elevation, let's say at about 2,500 feet above sea level. And then I need to come over here and look at my structure grid again. And I'll go now to my deepest formation, and this is the Dakota. And the deepest part here is just over 8,000 feet. I do have some well logs that go deeper than that. So let's say I want to go another 1,000 foot deeper. So that, we'll put in minus 10,000 feet here, which goes well below the base of my Dakota. So we have this. We have 12,500 feet of section that we're going to be generating a property model for. Now, the resolution here is based on the number of elevations and the number of stratigraphic depth samples. And because we have 12,500 feet, I want this model to be about 10-foot resolution. So, 12,500 divided by 10 means I need 1,250 stratigraphic depth samples, and I'm going to use 1,251, so just one greater, for my number of elevations. And that is all we have to do to set up this flow. And now we will choose an output, and this is a brick output. That's how we write volume files in here. And all we need to do is set the name, and then we'll click run. And this pops up a flow here, and this flow will take a couple of minutes to run, and then it will be ready for us to start manipulating and working with. Okay, so our flow is now at 100% in terms of its processing. Often what you'll notice here is it will stay at 100% for a little bit. And the reason why is that's because a lot of the operations are loaded into the back end of the flow. Things like, populating the model and writing the model out. So that's why you'll notice it'll be here at 100% maybe for an additional minute. But don't panic, as it will progress beyond this. Okay, so now our flow has finished running. Just for your reference, I am going to click here on the job log, and what I want to highlight here is the job log shows you how long it took for something to run. So this wall time, that is how many seconds it took to run. So we can see it took about 288 seconds to do the modeling, and it took about another 45 seconds to run this. So that took about 6 minutes in total. I did have the video paused there while it was running. But about 6 minutes to generate that 3D property volume. Now, what you'll notice is that it has written this file, pht_vol.vol, to our file tree. And I'm going to click on this, and what we will see is we've got this property modeling that's loading up. So the first time it loads up, it's a little bit slower because it needs to queue up here. And what I'm going to do is I'm going to scale this from 0 to, let's say, 0.35, and I'm going to give it a slightly more exciting color palette in here. So this is porosity. It's in decimal, so 0 to 35 is a reasonable range here. Now, I'm going to do a little bit of styling here so you can see what all you can do in this .vol file type. It's very similar to a .map. Here I can split the window, and I can add a 3D view, and I'm going to set the vertical exaggeration on this 3D view to 10, and you'll notice that we have this volume here. We can use our left mouse click and move to drag this around. We can also drag the surfaces here, so this is a full 3D model that we have here, so we can move this in 3D. And the first time coming through here, this will be a little bit slower because it is loading the volume into cache as we go through. But we have that option available to us. We can also, here we're going to split this window again, drag this over to a new view. We're going to add a map, and we're going to add some of our well markers into here. And this will kind of show us the area. So you can see that it tried to make the model over this much larger area, but data was only available here in this smaller area. We can hide that away here. Maybe we can add our property, and we're going to add our structure grid for the Niobrara in here. We'll add that in, and so now we'll have that as a reference as well. So there we go. We have that, and you can see we've got our 3D property model in here. It is loading up for us, and there we go. Now, what I want to do is I also want to show you how we can use this same flow to make other property models and how this will allow us to be faster and more efficient going forward. So I'm going to come back here to this flow. And if you remember in here, we selected our total porosity. I'm going to right click on this and I am going to make a copy. And this time, let's say I wanted to make a volume of my gamma ray. So I'm just going to call this copy gamma ray. I'm going to come here and I'm going to make sure to change the output name to gamma ray. And here in the logs to volume, you'll notice that there's no gamma ray curve that's appearing in here. So what we'll do is we will just type in gr_final. That's the name of the gamma ray curve that's in our log database. And then we can run this. And if I wish to make another flow here, and once again, I can just make a copy. And let's say I wanted to make a flow of my bulk density. So I could call this, rho B vol. And we'll hit OK there. Once again, we'll just change the name here from gamma ray to rho B. And we will type in rho B final here. Click create. And now we're ready to run that as well. You can have multiple flows running at the same time. So, if you're making 3, 4, 5 volumes, you don't have to wait on one to complete before you start the other. You can just run these in parallel. Now, I do recommend running one of them ahead of time, inspecting it and making sure that it works the way you would like in here. One other consideration that I would like to bring up here, which is right now, we have a number of inlines and cross lines in here. And if we look at our volume, we can see it goes from 498 to 1,000 for our inlines, and for our cross lines, it goes 132 to 787 in there. So quite a number of inlines and cross lines. If you wish to keep your geometry the same while reducing this, you can use the inline skip and cross line skip. So you can set that to maybe skip every other inline and every other cross line by putting a value of 2 in here and running that, and that'll make these files much smaller, which allows them to load up much faster and gives you a much smoother experience working with these, because this is a very large volume that we have just made, several tens of millions of grid cells. All right, so that is how we make a .vol file. And in our next video, I'm going to show you how we can add this to the .map that we've been working on as well. Thank you.